Hello, welcome to my talk on why we need to study inviscid and potential flows. In this talk, I will make introduction on the fluid dynamic equation, the Navier-Stokes equation, and the difficulties in solving the equation, and then a short discussion on the solution methodologies, and then move to why we need to study potential flows. And finally, I will give two examples for the applications of potential flow theory: the flow Partian airfoil and the wave structure interaction. In here, we take an incompressible flow as an example. For incompressible flows, the continuity equation is given as this. And we also have the momentum equations for three velocity components, U, V, and W. This momentum equation is derived based on the Newton's second law of motion. The acceleration vector equaling to the force vector, the vector F divided by mass. This part of the force can be regarded as the force per unit mass, that is, the acceleration equaling to the force per unit mass. Apply this law of motion to the fluid, we have the momentum equation as this. And for fluid motion, we have also the local acceleration, and we have also the convective acceleration, the body force per unit mass, and the force due to the pressure gradient, as well as the dissipations in the fluid. Principally, the Navier-Stokes equation is a perfect dynamic system. We have four partial differential equations, one from the continuity equation and three from the momentum equations. For solving four unknowns, three velocity components, U, V, and W, as well as the fluid pressure P. The big question is how we can solve the Navier-Stokes equation. In here, we talk the difficulties in solving the Navier-Stokes equation. The Navier-Stokes equations are second-order partial differential equations. This is from the dissipation terms. Navier-Stokes equations are nonlinear partial differential equations. The nonlinearity is come from the convective acceleration. For practical flows, the flows can be generally taken as average flow field plus the fluctuations, that is, the eddies of all sizes. But due to the non-linearity of the partial differential equations, the averaged flow and the fluctuations must be solved together. And we can see here, in practical applications, we have different types of flows. When the flow is slow, the corresponding Reynolds number may be small. Thus, the flow can be nominal. This is a type of smooth flow without any eddies. We have high Reynolds number turbulent flows, including the high Reynolds number flows with the energy carrying eddies from medium to small sizes. And we might also have extreme high Reynolds number flows, in which the eddies is very tiny. They are not energy carrying eddies. We might have intermediate Reynolds number transitional flows, this including the complicated eddies from very large eddies to very small eddies. We need to solve or model all the energy carrying eddies. Now we look at how we can solve Navier-Stokes equation for different flows. For laminar flows, we might have analytic solutions for some very simple laminar flows, such as coiled flows, Hagen-Poiseuille flows. And for more complicated laminar flows, we might need the numerical solutions for getting the answer to the laminar flow. We might have semi-empirical method, for instance, the air flows through orifices. And we may have potential flows. This is for the extremely high Reynolds number flows. It is equivalent to inviscid flows. This, including the irrotational flows, is a very strict assumption, but it works very well and very reliable for many practical problems, such as the wave structure interactions, the flow past airfoils at small angles of attack. For such a flow, the mathematics is very beautiful. And the very popular method is the computational fluid dynamics, CFD, including the Reynolds averaged Navier-Stokes equation, NANS, in which the turbulence models must be included for modeling the eddies. This is the most popular method. The problem is we might have the difficulties for turbulence modeling for low Reynolds flows, for fluid separations, etc. We might use large eddy simulations, LES, with modeling only for small eddies, while the large eddies is reserved. And the ultimate method would be the direct numerical simulations, DNS. This is a numerical solution to resolve all energy carrying eddies, from very large to very small sizes. So far, this is only for some simple low Reynolds number flows. In this talk, the potential flow is the topic. I will give more information on potential flow later in this talk. It is well known that currently CFD is the most applied solution method for both research and engineering problems. But why we still need to study potential flows? To answer this question, we will see the comparisons between the CFD and the potential flows. From the fluid nature, CFD serves the viscous flows, while the potential flow is only for ideal inviscid flows. But for solution method, potential flow has large advantages over the CFD. For instance, potential flows, the solving skills requirement are low. The solving time is very fast. The solution is very reliable, almost independent of the panels, while the CFD might not be very reliable, which might depend on turbulence models, the grid generations. And for understanding the results, potential flows is easy. However, for applications, CFD is for all flows, while potential flows is only limited to very high Reynolds number flows. Both methods would give the pressure distributions. However, potential flow will not include the wall shear stresses. It's only possible with some modifications. Both methods can be used for attached flows. However, for separated flows, CFD is only possible, but it still with significant difficulties, while potential flows is not suitable for separation flows. So we can see from the comparison between CFD and the potential flows. Both methods have their own advantages and disadvantages. For practical reasons, we might choose different methods for different requirements and for different problems. Here, I would like to give one example for why we need to study potential flows. This is a famous textbook by John D. Anderson, Fundamentals of Aerodynamics, 6th edition. The book contains 20 chapters, and the first 2 chapters are for the introductions of fluid dynamics, with total pages 1078 pages, 202 pages for the introductions. If we examine the inviscid flows and the viscid flows based on chapters, in the book there are 12 chapters for inviscid flows and 6 chapters for viscid flows. So we can see the inviscid flows would take 66.7%. If we examine the contents on pages for inviscid flows, there are 720 pages, while the viscid flows, there are only 156 pages. So inviscid flows would take more than 82% in pages. Therefore, we can see for the fundamentals of the aerodynamics, the majority of the content is for inviscid flows. And if we look at the more advanced book, Aerodynamics for Engineers, 6th edition, by J. Burton and R. Cummings, the book has 14 chapters, 2 for the general introduction of fluid dynamics, and 801 pages in total. 97 pages are for the general introduction. On chapters, the inviscid flow has 7 chapters, viscous flows 7 chapters too. So inviscid flows would be in percentage of 50%. And on pages, inviscid flows have 473 pages. Viscous flows have 375 pages. So inviscid flows take about 56% of the pages. So again, we see even for the advanced aerodynamics, more than half of the pages and the chapters are paid for the inviscid flows. So from these 2 examples, we can see inviscid flows, or more specifically, the potential flows, are very important. Now we have a look at the fluid dynamic equation for inviscid flow, that is Euler equation. For incompressible flow, the continuity equation is given as this, same as that we see previously. And the momentum equation would be given as this. The difference between Euler equation and the Navier-Stokes equation is, in Euler equation, the dissipation terms vanish since the viscous coefficient mu is 0, thus nu is 0 too. So this term would vanish. And the same for the momentum equation, we have local acceleration, convective acceleration, body force per unit mass, and the force due to the pressure gradient. It is similar to the Navier-Stokes equation. This is a perfect dynamic system. We have 4 partial differential equations in Euler equation, and these are for serving 4 unknowns: velocity components u, v, and w, and the pressure P. The advantage of the Euler equation over the Navier-Stokes equation is The values for Bernoulli's equation is an integral form of the Euler equation. Euler himself derived it in 1752. Euler equation is the first-order partial differential equation. Hence, numeric solutions would be slightly easier than Navier-Stokes equation. Otherwise, Euler equation and Navier-Stokes equation are same, especially for the non-linear convective acceleration. Thus, the solutions for Euler equation would not be easy. Even the fluid viscosity is considered as 0. The most famous inviscid flow would be the potential flow. These potential flows are the special flows of the inviscid flows. The fundamental assumption for the potential flow is the flow are rotational. Mathematically, it is given by the core of velocity vector is 0. Here, velocity vector has 3 components u, v, and w. As we have mentioned, the assumption for rotational flow is quite strict. Why is this? If we have a look of the core of the velocity vector, it would be calculated as the determinant given as this. Here, the unit vector I, unit vector j, and the unit vector k are the unit vectors along x-axis, y-axis, and z-axis. So if we calculate this determinant, we have the expression as this. This part is for the component of the core of the velocity vector along the x-axis. This is the component along y-axis, and this is along z-axis. To make this vector to be 0, that means all 3 components must be 0. That is, we have 3 equations for 3 components of the velocity vector v. So, under the assumption of rotational flow, the fluid velocity components are not independent of each other because they are linked with these 3 equations. One question would be, is this assumption correct for flows? From the assumption of the rotational flows, they exist a scalar function phi, and we define the flow velocity component as this. And then this scalar function is called velocity potential function, and it would guarantee the flow velocity component to satisfy the assumption of rotational flow. Since we calculate the component around x-axis for the core of the velocity vector v, and we substitute of the component into this, and then we can see the result for this expression. It is 0. Here we can see these are same, only the order of the partial differentiation is different. In mathematics, this makes no difference. Similarly, we can calculate the component along y-axis. Again, it is 0, and the component along z-axis, it is 0. This makes sure the core of the fluid velocity vector v is 0, because all 3 components of the core are 0. And if we use a special mathematical operator, the velocity vector and the velocity potential function would be given in a more compact form, given as this. Here, Laplace is the operator for the gradient. which was introduced in 1837 by the Irish mathematician and physicist William R. Hamilton. The symbol was resembled to Irish instrument, the Irish harp. See this. And we can see a simpler proof of the core of the velocity vector is 0, since we substitute the expression of the velocity vector into this expression. We can prove the core of the velocity vector is 0, since a core of a scalar gradient, this is 0. So we can see we have one advantage for potential flow. For potential flow, we don't need to solve all three velocity components u, v, and w, but solve a scalar function phi. So this is one of the advantages of the potential flows. The dynamics is reduced from three velocity components to a scalar function phi. To build the dynamic equation for the potential flow, we can apply the continuity equation. Here, the flow is incompressible, so the continuity equation is given as this. If we substitute the expression of the velocity component into the continuity equation, we have the expression as this. And we can write the equation as this, or in a compact form, use the Laplace operator given as this. Here, Laplace squared is the Laplace operator. So here we can see another advantage of potential flow. The Laplace equation is a linear partial differential equation. This could provide a possibility to solve the equation using the superposition method. Of course, if the boundary conditions are linear too. This is true for many practical problems. Having talked about the advantages for potential flows, in the next two slides, I would give two examples to show how good the potential flow theory can be for some specific flows. The first example is for the flow past an airfoil, the airfoil E387, based on the reference here. The comparison is made for the method X-foil, which is basically based on the potential flow theory with the modification for including the wall shear stress and the three other CFD simulation, K-omega SST turbulence model and the K-omega SST low Reynolds number turbulence model, and the three equation K, KL omega model. So for the lift coefficient, the CL, we can see X-foil predict the lift coefficient very close to the experiment data, even at the high angle of attack. See here, X-foil predict quite a good result against the experiment, even better than the CFD prediction. The second drawing is for the lift coefficient against the drag coefficient, and from the plot we can see X-foil predict the curve better than most of the CFD result. This is a very interesting comparison. It should be known this publication is quite new. It was published in 2016. Therefore, potential flow theory can be still very useful if we want to calculate the lift coefficient, especially at the small angle of attack. The second example is the modeling for a wave energy converter. a fixed oscillating water column wave energy converter, C, this cylindric OWC. This is fixed on the frame. This is the pressure response in the water column. And we can see the experiment result and the numeric simulation are very close. This is the water surface in the water column. Again, the numeric modeling are very close to the experiment data. So in this numeric modeling, there's no additional damping for the motion of the fluid. Therefore, the only assumption for the potential flow is the flow is irrotational. And you can see again, the potential flow give very good result to the fluid motion for wave energy converter. This is very useful because if we use CFD for modeling this type of the wave and structure interaction, it is very difficult because the free surface and we need to use very fine grid at the free surface and it is time dependent. So the conventional CFD for modeling such a wave structure interaction would be very difficult and very time consuming.